Hello, welcome to the lecture series on vehicle dynamics. In this chapter, we will discuss about excitation sources and vehicle responses. We will identify various excitation sources. We'll develop model for excitation sources. Then we'll discuss the effect of these excitation sources on vehicle. And let us discuss and arrive at right suspension frequency and suspension damping ratio for the vehicle. Also, let us understand vibration isolation and vibration damping in vehicles. So one of the most important criteria of vehicle dynamic design is to achieve good comfort. Comfort is to do with ride. So we know vehicle, we model it as simply a spring, mass, damper system. You know this is called sprung mass. This is called unsprung mass. And this is our tire. We model like this. This vehicle will be subjected to various excitation sources. Suppose this is the wheel of the vehicle. As it travels over this road, it will be subjected to some kind of excitation. So now the thing is, how exactly to this excitation this vehicle behaves is the question. Okay, it exhibits vibration in response to excitation inputs. Vehicle vibration response determines the magnitude and direction of vibration imposed on the passenger compartment and determines the passenger perception of the vehicle. Okay. So let us understand which are all the excitation sources. Then after understanding all the excitation sources, let us express the excitation sources in the form of an equation. Okay. Then we will develop the model of the system, that is the vehicle. Then this excitation equation, that is excitation model, we will solve with the vehicle model. Then we will get the response model. Then we will, from the response model, we can interpret and find how exactly the system is behaving and how human perceives the whole thing. That's what we are going to do. In simple words, it's very this thing. This is your, say, vehicle. I'm going to give the inputs to this vehicle in the form of an equation. That is what you call it as excitation model or excitation equation. This is the vehicle. Get the vehicle equation or vehicle model. Then after that, solve this vehicle model for this input. Get the response model. This is what is important. Okay. Fine. Then To achieve the required response, what needs to be done within the vehicle, what parameters have to be tuned in the vehicle so that the response is pursued by the human as comfort. So I think probably I have given much more detail here. The road surface irregularities, then the dynamic structure of the vehicle response to excitation. That's what I already told. Again, you can see the road holding ability of the vehicle, one part of it. And the second, this thing is how the human pursues this response is the second part of it. So what are those excitation that come to this vehicle dynamic system? The road roughness, this one, tire wheel, from there lot of excitation comes, drive line, lot of excitations will be coming from there, also from the engine. This is what the input we give. And you have the vehicle model. Correct. Now response. What parameters to be tuned so that human pursues it as comfort. Okay, we'll talk about this part. First, let us look at these modeling excitation sources. First, let us look at the road surface modeling. We have different types of roads, that is local, then collector, arterial roads like this. So you'll have many local roads, okay, like this. Each one is a local road. Okay. Then you can have again a collector road like this. This you can call it as a collector road. Local roads, local. Okay, like this. Then you can have, arterial roads. Go connect here. Go connect here. Go connect here. Similarly like this. So it's the main artery. It's like this, blood collection at the local point to the main, like this. Okay, this you can call it as collector roads. This you can call them as local roads. This you can call it as arterial road. Okay, fine. That is a different types of design for different speeds and all that. And if you look at each road, the road surface, something it can be like this, like this, like this. These are all various types of road surfaces that you come across. So we cannot take the vehicle every time test. We should be able to, varying certain parameters in our model, we should be able to replicate any of these roads. Okay, and we have to develop the model like this. Model means equation. So one of the way we talk about is road power spectral density. What is that power that signal contains in a given frequency range? Okay, suppose this is the frequency range. delta, say delta omega frequency range. Within this frequency range, what is this? Okay, this signal, what is the power it contains? That's what exactly we have to find out. That is what we call it as power spectral density. Using this as an idea, it is possible to develop a model for the excitation sources. So we can mount accelerometer on the vehicle, and there are various ways of collecting the road profile. Okay, we can run the vehicle, the sensor, and we can obtain the road profile. You see here acceleration versus time graph we can obtain. Also acceleration versus distance is possible. So the displacement you can define Zz equal to Z naught sin omega t, where omega is angular frequency radians per second. When you draw this graph with respect to time. If you draw this graph with respect to distance, then you can call this as spatial frequency. Correct? In a given length, what you can say here. Here, actually what we do is, when we have a wave, sinusoidal wave like this, we get a time period, and 1 by time period we write it as frequency, correct? So in this case, time is the x-axis. If instead of, sorry, time is the, okay, x-axis. Instead of time, this is space. X, this can be written as 1 by L. That is what we write, 2 pi by L. Then we call that as a spatial frequency. Okay, spatial frequency. G I have written for the ground, Z naught sin omega x. Okay, now what I can do is assume this becomes, I want to get a vehicle power spectral density. You see here power spectral density, by definition it is defined like this. Okay, power spectral density by definition is given like this. Okay, this value divided by range of frequency, that I call it as the power spectral density, Sg. So this you can call it as vehicle power spectral density. This is the transfer function of the vehicle. Okay, this is ground power spectral density. Okay, how you get this? Vehicle can be modeled as S omega n square divided by S square plus 2 zeta omega n S plus omega n square. Right? Maybe you are getting little different. Anyway, I can say this, it can be modeled. One minute. Right. So now I can write this as spring damper. Okay. Okay. And that is the displacement M K C. Okay. Now this is LQF of T. Then writing the differential equation, and if you find a transfer function, I can reduce it to this form, right? So this equation represents system. This represents the power spectral density of the excitation source. Then I should get the vehicle power spectral density. Now for that, let me demonstrate this. This is the acceleration versus time graph that we have opened. GRMS value is overall 1.49. This is in the frequency range 10 Hz to 40 Hz. Okay. Now I'll take a filter, say band pass filter. I'll obtain from this, I extract a graph, accelerations versus time graph 10 Hz to 20 Hz. And I also get the GRMS value. Then from this I get this one, that is from 20 Hz to 30 Hz. Again the remaining I'll abstract from 30 Hz to 40 Hz. So I know GRMS values, also bandwidth I know. Let me fit an equation now. So 10 Hz to 20 Hz is 1. The midpoint of that band center frequency is 15. GRMS value I have calculated, it is 0.68. Square of GRMS value is 0.46. Divided by bandwidth is 10. This divided by bandwidth will give you this power spectral density. Okay. Next, for this range I will do the same thing. For this I'll do the same thing. Now I got 1.15 at 25 this, 35 this. Okay, this is power spectral density versus frequency. I can fit an equation now. Okay, I'll get this. So very easy. I'll just fit a polynomial, saying I know these are the x values, these are the y values. So I'll try to fit a equation. Maybe y is equal to a naught plus a1x plus a2x squared. Correct? Like that, I'll fit a polynomial. I'll find a naught a1 value and I'll get my equation. Y is nothing but my acceleration. That is the input. Okay, right, sir. So instead of acceleration, you call this as maybe SG. You get this equation. So here he has given SG values, value into 10 to the power meter square per cycle per meter. If this value is less than 8, geometric mean is 4, it's a good road class. It is between 8 and 32, it is good road. 32 to 128, it is average, poor, very poor. If you are having this kind of power spectral density, then it is, I think that roads are very, very bad. So here it is given power spectral density values versus spatial frequencies. Okay, smooth runway, smooth highway, gravel road, a rough runway, like this. So in the range they are given these values, how they vary and within what per frequency, because it is cycles per meter length, that is also there. So that is spatial frequency, correct? Right. So based on power spectral density, you can classify the roads. So road modeling, I was talking about this kind of experimental way we can find out. Also there are, giving the data that is basically a 2D one single track. You want to create a 3D road. There are softwares available and we can create 3D road models. So one of these is called 3D track. So it's possible collecting the data from various sensors, you can say, we can create 3D road model. You can use, if you have a vehicle model and if you have a road model, it is possible for us to run this vehicle on this road model and study its behavior. So in software like Adam, we can do this. Okay, Adams. There are many such softwares available. Probably we can create a model in MATLAB, road model, and if I know the vehicle model, we can solve the equation and we can study the response behavior. So you can see 3D road models are available in Adams car and you can choose this. Okay. Now you see here, road roughness as an acceleration input. Meaning is this. What is this we are talking about? This is the acceleration. We are taking all this model, we are modeling this in this form. That is the input to the vehicle. Road roughness as an acceleration input. The roughness in a road is the deviation in elevation seen by vehicle as it moves along the road. Like this. So this is what I'm talking about, the elevation part of it. This is the roughness. Okay. So this will, if you have a wheel, as it rolls over, it results in vertical displacement input to the wheels. And thus that will lead to vibration, ride vibrations. Okay. So now again it will produce accelerations in the vehicle. So if this is the sprung mass and these accelerations are produced, I think on each person sitting over here, this acceleration value and the mass of the person is going to be the force that is going to be imparted to the person. Okay. Okay. So while developing the equation is saying, assume a speed of travel, convert elevation profile. These displacements, take that, convert elevation profile and differentiate, and you will get the velocity. If I differentiate once again, we get the acceleration. Yes. So from here we can write that equation. Okay, right, sir. So that is from the road excitation. You have excitation coming from tire and wheel assembly. Okay, now what happens? Suppose you have tire. So mr omega square. Suppose there is an imbalance force m, or it is the radius, omega is the angular speed. So you will be getting a kind of a, periodically a kind of a force, centrifugal force hitting the vehicle. Okay, so we will be getting that kind of situation we'll get. So that is what mr omega square, imbalance force, imbalance magnitude, rotational speed with radians per second. You will get this. Okay, so this we can plot like this if you want. There is a problem here also. You see here, we model tire as a set of radial springs. Stiffness of each spring is not same. So when it is rolling, correct, now the height portion of it, if you look at, so suppose I say this is the wheel. When it rolls, the center point you see here, it should go only along this line. It may not happen like this. Here, go down like this. Maybe displacement is more. Correct. Displacement is like this. This is the kind of thing. So it will be following this path instead of following an horizontal path. So that will also become an excitation because of the variation in stiffness. This tire has certain natural frequency. As the speed changes, excitation to the tire also changes. So it starts vibrating. There will be number of eigenvalues. So when it is start vibrating with first harmonic, probably you'll get an eccentric. So imagine this eccentric wheel rolling on a flat road. At a second harmonic, it may become simply oval. Now imagine what can happen. Say third harmonic, fourth harmonic. So like this, a number of excitation forces will start getting into it. Okay. You can say that at a particular, when it starts resonating, even the wheel take the shape like this, standing waves. So I told you about the stiffness variation and all these things. So all these can be modeled. Correct? So we can find out how exactly the variation happens. Another thing is we use drive line. Here you are using universal joints. Universal joint. So we are transmitting motion at an angle. So when we see, the driving shaft will be tracing a circle. Maybe driven shaft will be tracing an ellipse like this. So here the angular velocity will not be uniform. And omega is not uniform, then automatically alpha comes into picture. That is angular acceleration comes into picture. Acceleration is there, then there is going to be a force. So these are what these forces create excitation. We call that as a driveline excitations. Sometimes to cancel this, we introduce one more U joint. Correct? Then it will be smooth if it is completely cancelled. Otherwise, we will have this kind of difficulties. Okay, that is what it means. Okay. Similarly, torque developed by this will not be uniform. That's why we go for multi-cylinder engines. If a perfectly balanced engine may not create a lot of excitation, if the engine is not perfectly balanced, then we will be getting the torque variation. Correct. So these are all the excitation forces that act on a vehicle. Okay, now you have road roughness, that using PSD idea we can model that. Then you have wheel excitations. Then we have driveline excitations. Then we have engine excitations. These are the kind of inputs that act on this. Now vehicle as such, we can model it as, yeah, you know that many times I have spoken about this. This is the sprung mass. This is the unsprung mass. This is the suspension part, and this is the tire model. Okay, now we will give excitations on this, and we will study how sprung mass, unsprung mass behaves. Okay. In automobile language, one of the most popular model, we call it as quarter car model. Suppose this is my vehicle. Okay, if this is my vehicle, okay, let us take this part of it and we will model this. That's what I call it as a quarter car model. That is sprung mass, unsprung mass, okay, road. That is suspension stiffness, suspension damper. This tire stiffness is unsprung mass. You see here the road excitation using power spectral density model that can be given as input here. Wheel excitation can be given as input here. Road displacement, wheel excitation. Because it's a chassis wheel mounting transmission and engine, that excitation is here. Correct. Now the behavior of the vehicle we can study by writing down the differential equation. Okay, Z is the displacement of the sprung mass, ZU is the unsprung mass displacement, and ZR is the road displacement. We have to differentiate and then get acceleration there. Okay. First, you see here, this Ks and Kt will take. Compared to this mass, this mass is negligible. Small m is very small compared to capital M. That's why we can write this is Kc and this is Kt we can write. These two springs are in series. That's equal to resistances in parallel. So 1 by Ks plus 1 by Kt is equal to 1 by K. So K equal to, from the previous one, Ks Kt, Ks plus Kt. Okay, this is, you call it as roll rate, sorry, ride rate. Please call this as ride rate. Okay, now next. Bound's natural frequency of the vehicle. Root of K by M. Natural frequency of the sprung mass. Here RR by M, the quarter car mass. Okay. So this is how we can find out this. This is the natural frequency. Natural frequency will be again, you can write it as 1 by 2 pi root of RR by W by G. I'm talking about quarter car. You will consider only for that quarter car, that part of it. Yes. In vibration, we have studied damped natural frequency is equal to omega root 1 minus zeta square, where omega n is natural frequency, and damping ratio zeta is equal to actual damping by critical n, that is nothing but this 2 root km. So you can also see that you should, on a stationary vehicle, a static deflection of 10 inch if we can obtain, then the corresponding natural frequency will be 1 hertz. That's the thing. So now what we do is, I have taken this system. I will write one differential equation considering this part, and I will write another differential equation considering this part. That's what I have shown here. Okay. Now on the sprung mass, you can clearly see that there is inertia force, that is 1. This is suspension stiffness force, damping force 1, 2, 3 plus 1, 4 forces should be acting. Only FB is acting downwards, all other forces should act upwards. Yes, FB, 4 forces. Inertia forces oppose the motion. This is stiffness force. This is damping force. The second part of the system, if you see, you have suspension. This is stiffness force. Then inertia force you have 1, 2, and these two forces 4, and this wheel excitation force 5. I should show 5 forces. Yes, done. Here 5 are there. Now we can write the differential equation. Only thing is, while writing, I have substituted S is equal to J omega to convert into frequency domain. Here I have taken sprung mass acceleration to road acceleration, because that should be taken as input. Then I will get this equation. Here sprung mass acceleration to that is wheel excitation, right? That's what I have taken. So force by mass is nothing but acceleration. Here this one FB is nothing but here this one body force. So those excitation I have plotted. Okay, for simplification sake, we have done all these things. It is not difficult. We can use even Simulink and we can plot all these response curves. Correct. Now, one of the response curve that we are getting is this one. For the road excitation, the double dot and all that. This response is showing a peak value. Sorry, I have to draw a vertical line. Peak value somewhere at this frequency. Okay, that's the peak value. That comes the value as 1 Hertz. Please note that while designing the vehicle, we always keep the natural frequency of the vehicle as 1 Hertz. This I have explained when I did the introductory topic. That's why that corresponds to something I have said around 10 to 15 kilometer speed of the vehicle. So that is the reason why the response is showing a peak value at 1 Hertz. Okay. And this curve, if you look at, this is because the body force and all that. So slightly at little above 1, it is showing an excitation. Otherwise, whatever be the frequency, it remains constant. The 1Z divided by FW by M, wheel excitation, it shows a peak somewhere around 13 Hertz. 10 to 13 Hertz. Around it will show like this. Sorry, 12 to 13 Hertz. This we call it as wheel hop resonance. Wheel hop resonance. That means this is the unsprung mass natural frequency. Somewhere at this point. After that, this decreases. Here also it decreases. Okay. All right. So normally, if you fix this idea here is, if you fix this as 1 as the natural frequency of the system, you can very clearly see that at higher frequencies, the response gain is low. That is, acceleration output is low. And the force that is acting on the occupant will be low. Correct. Only at something wheel hop resonance acts at a 13 Hertz frequency. Right. Otherwise, normally it will, as you increase the speed, the response gain will be very, very small. And occupant will start getting more and more comfort as we increase the speed of the vehicle. Okay, that's what the meaning is that. So same thing which I explained it. Another very important thing you may say, If we had set sprung mass natural frequency other than 1 Hz, if we make it 1.25, 1.5 or 1.752, you can see here mean square acceleration becomes very high. So it is better that we play around within 1 Hz. Correct? And another very important thing is the damping. This also I explain. It is better to maintain around damping value of 20 to something like 40%. There is something like Jones stroke, you maintain 20%, and bone stroke you maintain 40%. If the damping value is very low, 10%, you can see the response gain at something like at same at 1 Hz is very high. Maybe at other frequencies the value will come down. If it is 40%, response gain is small here at 1 Hz. As the frequency increases, it will be very low. If I maintain probably 100%, that is critical damping, the response gain may be low here, but it remains large value for a higher range of frequencies. And if you use 200, you see it's very bad here. So that is the reason why we play around with 20 to 40%. Okay, so that's why we use dual rated dampers and other things. I told you about wheel hop resonance frequency. So here axle weight comes into picture. Correct? It occurs around 10 to 12 Hz. I think for a good behavior, okay, you can see here if you use very heavy unsprung mass, the typical one is somewhere here at 13 Hz is showing some response. If it is very light, it is like this. It is heavy, it is like this. So normally, I think I have shown the percentage. For non-driven axle, the weight W is typically non-driven. Okay, non-driven axles, W is typically 10% of the gross vehicle weight, whereas drive axle it will be about 15%. Gross axle weight rating. Okay, right, sir. So 10 to 15%, that's what we are playing around. So another very important thing is you see here, so in this case resonance frequency RMS acceleration at 1 Hz, this is the response value. As the frequency increases, it starts decreasing and it remains constant, but again at higher frequencies this value keeps increasing. So that is why if you operate at this range, so acceleration value keeps decreasing like this. That's why we need to isolate our frequencies. Okay, rate simulation, we can do 4-poster analysis. Sorry. Okay, I will 4-poster. we can use, we can do the simulation, also we can test for various conditions, correct? Then we can go on tuning the parameters. So and we can reduce the effect. So here I have done bump, hue, pitch, power spectral density, roll, all this. Okay, 1 minute. This is pretty old. The present day drivers are not supporting. Okay, all right. So using PAC 2002 model, correct? Tire model that is used. Okay, fine. If you have a copy of the, license for Adams, you can really play around with this kind of simulation. Let us talk about something like spring and wheel rate. So you have a suspension spring. What is the force coming under suspension spring? And what is its deflection? That will give you spring rate. One end we are connecting, this is a lever. Here you have the spring, and here we'll have the tire. So when you apply this force, how much it will rise? Load acting on the wheel divided by rise of the wheel. So that we call it as wheel rate. Okay, now you see here. Okay. So to understand this, it is like this. Okay. Let us say its vehicle frame is a spring. Okay. So this fellow is supporting the spring mass. So load coming on the wheel is there. Okay, that load is FA. Let us say the load that is coming here is FB. Okay, right. Now basically that FB will be acting like this. Reaction. So FB into B. Is equal to FA into A. So FB is equal to FA into A by B. So now the displacements you can say here, this is a dA. Okay. Now FB, you can replace this by dB. dAB by A we can write because it's proportional. If I divide one by the other, I'll get like this. So this you call it as motion ratio. A is smaller than B. So when you square it, Yes, that will become, this is less than 1, square it will become smaller, and kb will become smaller, right? So what is the idea of this motion ratio? Okay, the force transmitted to the body is reduced if the motion ratio is increased. Correct? Huh? The force transmit, because load is transferred to the chassis from the wheels, that we have studied. So force transmitted to the body is reduced if the motion ratio is increased. Okay. Okay, the motion ratio describes the displacement ratio between the spring and the center line of the wheel. The motion ratio squared times the spring rate gives the wheel rate. Okay. Travel along the spring axis, vertical travel of the wheel center line. So spring rate equal to wheel rate, okay, by motion ratio square. Okay, sir. So that's how now this gives you an idea where exactly the spring has to be placed, the spring and the damper. So once I fix the motion ratio, whether the spring should come here or here or here, we can decide. Okay, that is the advantage of this. So to achieve that 1 to 1.5 hertz frequency, there is a thumb rule. It is better we should have the wheel rate value within this range and the spring rate value, okay, is this. So these are some of the hints that is given where it should be. Critical damping, what is the value it's talking about, where exactly the damping coefficient must lie, right? So these are some of the hints that are, again, roll stiffness. Okay, the thing is, the springs, not only, they should also provide the roll stiffness. So these are all the things where exactly the value should be, roll stiffness value should be. Okay, these are all some of the equations, approximate equations available for fixing the values to get the performance, better performance. Okay, so that is about more the excitation source and response of the vehicle in vertical direction.